Huh?
It's the UFOs trying to contact Mr.
It could be. I don't know anymore. So again, just make sure you put a title. Include the unit. So in this case, it'd be seconds squared. Meters here. Okay. And then you draw the best fit line. Some of you were not aware of that either, but the best fit line, in this case, you know with certainty it passes through 0. But you draw it such that, I'm going to draw it first and then I'm going to add some dots. Draw it such that there's equal amount of data on both sides. It can be a very rough drawing sometimes. Not going to be very accurate. And then the title is T squared versus L. So it's this, that's called the dependent variable versus the independent variable. I'm just going to be back in a second. My stomach's upset. I'm eating too much spicy stuff. Sorry about that. Take a little break. Not going to hurt you. Oh, gosh. Be back.
Like 2, like 3. It's 1.5 hours.
Oh.
Like, something like that. I'm trying to do one get I already got it like several weeks ago.
So it wasn't.
Well, now it's full. No, you just show up.
Yeah. Test is tomorrow.
Oh, I'll give you questions.
Why?
You can ask me questions. Any questions? Total kinetic energy is converted into a region momentarily in one region. Okay. So it'll be attracted to 0. It will be attracted. Since it's like positive, all of them are positive, so they won't want to keep on going. So 0 will go very fast. Okay, there's no numbers on here, so like you can, there's like no length or anything, so you can actually just guess. So it goes into 0 really fast. It goes past 100. It goes past 200. It goes past 300 and then 400. So something like this, you just have to like understand the thing. Oh, I see. So between this and this, it's pushing forward. It's being pushed back, but then between this and this, it's actually being like pushed this way and pushed this way also. But so then this should actually just be a difference of 100. A difference of another 100.
No, if you extend the pocket, it's gonna go to like.
Each of these segments has
Wait,
a
is it an
difference of
electron
100 volts.
It's gonna go up. If you learn the power
All
down.
This one wants to push back, these want to push to the center. So 100.
Oh, so I guess like.
If you have that much kinetic energy, max
Yeah.
kinetic energy also equals potential energy. Yeah, change it to like, so that equals EPA times Q. Okay, so, alright, so change in potential energy equals EPA times Q. Each of these has an EPA of 100 times Q. Q is a photon. That means it has, oh god, what is that? Photon and charge is 1.6 times 19. Times 100. 16 to power 1.6 times 10 to the power negative 17 times 2 equals 3.0. So then you'll end up using, I think L, I think L. 15 Which one is that? It is 15 Oh, yay, you did it.
Yeah.
Okay, so you see, the difference between each of the plates is 100 volts. Because that's one,
Okay.
because this one, difference
Got it.
in charge equals potential energy, which is also.
Okay, so, hey, gents, let's just revisit this. So that's one thing that stood out in the labs. Just make sure you set up the graph properly. So I mean, if you missed units, I deducted like a half mark off for that. Also, units, how do you find the units for your slope? So units for slope. Okay. Same way as you find the slope, rise over run units. So this is the units for the rise. In this case, it's seconds, and this is the units for the run. That's seconds over, seconds squared over meters. That's it. Yeah.
So in a way, meters is determined in a second.
Say it again.
So the one on the x-axis is the.
Yeah, in the denominator.
Yeah.
Yeah, whatever unit is on the y-axis is in the numerator, and whatever units on the x-axis is in the denominator. Okay, so now we can go over page 372. Okay, so page 372, number 1. Okay, so just read it over to yourself. Yeah, okay, so what's flux? That's the question. So remember, flux is that's flux. So what is, before we move on here, just so you're clear on what this angle is referring to, it's the angle, if I draw this coiled loop or this rectangular shaped coil of wire. Okay. There is what we call, this is the surface here, by the way. Let's make sure we get that clear. This is the surface. There is a line that passes. It's probably not as clear as I should be. Make it yellow. There's a line that's perpendicular to the surface. Okay, that's the normal line. Okay. So it's the angle that the magnetic field makes with that. The magnetic field, in this case, magnetic field is that way. Yeah, I better draw it properly. Sorry, I'll try to be more exact. Come out from under here. It's the angle that the field lines, the magnetic field lines make with the normal. So in this case, the field lines are parallel. So the angle in this case is 0. Okay. Cos of 0 is 1. So that top equation would just reduce to and that's what it is to start off. In most of our problems, the field lines are parallel to the normal line. Yes, this should read normal. So if you turn that same loop, you rotated it. Let's see if we can do that. I'm going to change a couple of things here. Rotate it like that. Don't copy it yet, please. So that the field lines are now perpendicular to it. Perpendicular to the normal. This angle here is now 90 degrees. Cos of 90 is 0. In this case, that's 0. 0 times anything is 0. Flux is 0 in this case. Just so you're aware of that. Okay, let's get back to number 1. So we need to calculate, it's a circular loop. We need to find, obviously, again, with the flux, we need to find the area. Remember, that's 1. Area is pi r squared. We're told it's a circle, a radius 5 centimeters. So that works out to be 7.85. Okay. So the flux then is just simplifies to just B times A because the cos is 1. Magnitude is 3.2. Magnetic field is 3.2. Area is 7.85. Okay. I don't think this is right. I got 2.5 times 10 to the negative 5. Yeah, okay, that is right. Yeah. That makes sense. 2.5 times 10 to the negative 5. And it's Weber's or Tesla's meters squared. Two. Read that to yourself. Okay, so let's calculate the change in flux. Final minus initial. Final is 0. What happened? Oh, thank you. I don't know. Okay, happens, I guess. Did it just happen? Okay, so the final flux is 0. We're told in the final case, you look at what it says, the coil is parallel to the field, so it's like this in the final case. So the flux is 0 at that point. 0 minus B times A. The cos in this case initially is 1. So we need to find the area. We need to find this area. Area is equal to pi r squared. In this case, it's 6 centimeters. And it's 1.13. Meters squared. Magnetic field is 3.6. times 1.3 or 1.3. And this works out to be negative 4.07. Just carry an extra digit. You can round it to 2 at the end. It's Weber's because it's flux. And then the induced voltage is just the number of turns times the change in flux. I'm just rewriting the equation. That number of turns is 200. Change in flux is this. And it does so in 0.015. Okay, and the answer is 0.054 volts. Remember, this is a voltage. It's an induced voltage. It's got a special symbol, but it is a voltage. Okay, read over 3. I'm going to go over all of these. Some people tend to have problems with these, so I'm taking my time with it. Yeah.
When it starts with time zero, it's perpendicular.
Yeah, it's perpendicular to the area. It's this, right?
It doesn't mean it starts perpendicular.
It starts like this. That's the initial. And that means you've got a cos of 1. That's initial. That's final.
But it says that time zero is perpendicular to the field, so that means that's initial and that's final.
Yeah, let's read it carefully. The coil is perpendicular to the field. So this is perpendicular to the field.
That's
The
perpendicular.
area, what they're saying is the area is perpendicular to the field. Yeah. That's what they mean. That's parallel. It's parallel. The area is what they're referring to.
Okay.
Is parallel to the field. Yeah.
Ooh, okay.
Does that help?
That's-
Yeah. Yeah, I know it's a little confusing. Da-da-da. So in number 3, if you read it, let's look at it. A is the initial case. There is a flux in A. There is an initial flux. And so let's calculate it. And we know we're going to have to calculate it. So remember in this case, what's the direction of the induced EMF? We need to calculate the EMF first, right? So we'll do that first, and we'll talk about the. We'll calculate the EMF first. And then we'll talk about direction of current. We'll do that after. So we need the final and initial. We know, looking at the diagram, there is an initial, there is a final. Initial is pulse is 1. Because the field is, it's this situation here. That's the initial, same as before. So the angle is 0. I think I put cos of 90. It should be 0. Okay. So initial is simply BA. Okay, and the area we're already given, that's good, that helps us. Magnetic field is 2.2. Area is 2.5. That works out to be 5.5. Okay, our initial. Final. Okay, final is basically this, just another way of drawing it. The field lines are parallel to the enclosed area of the loop. So in that case, the angle between the normal and the field lines is 90, so the flux is 0. So just rewrite it. So in this case, number of turns is just 1. A change in flux is 0. Minus the 5.5. And it's all done in, we're told, 0.1 seconds. So that works out to be 5.5 volts. Okay. Now I got to show you which way to induce current is. So you go from this is what you go from. Now draw the magnetic field in pink. Actually, let me circle this first, and then I can make a quick copy of it. So you go from the top version, this is what you start with initially. To this, essentially there's no magnetic field pass. I know it's parallel, but there's no magnet. The point is there's no magnetic field cutting through the area. So that's your final case. Nothing cutting through it, no magnetic field cutting through it. But you need to always preserve the original flux. In simple terms, you want to retain the original amount of X's. You can think of it that way. As much as possible, you try to preserve it. The way to do that is to create a field that's into the page like it was before. You want to get back to that. So which way would do that? The current running this way. Remember, we're interested in which direction the fingers curl on the inside of the loop, not on the outside. We can deal with the outside later. We're interested always on the inside of the loop. Which way would the field point via current? Okay, let's guess. I'm just going to guess. What do you think? Should I go clockwise or counterclockwise or clockwise? Yeah, okay, try clockwise. We'll try counterclockwise after. So clockwise would mean that the current's going this way. You're always revving forward. You're curling forward. On the inside of the loop, that would mean that the fingers point into the page, which is what we want. So that's the correct area. Yeah, the current is clockwise. Oops. Current is going to be yellow. That's the direction of the current. That's the direction of the current. That would result in magnetic field on the inside of the page this way. Let's just look at the bottom. That's what we're interested in, the inside of the loop, not the outside. On the outside, it gets confusing. On the outside, it actually would be coming out of the page. The coil's around. But we're interested in this portion here. You want to get back to this as much as possible. That's what nature tries to preserve. Yep.
So then, like, once it collapses, doesn't matter how much area there is. Like, it's still just have like a tiny amount of area with like a lot of like a really dense amount of magnetic charge.
Yeah, that's right. You mean you're talking about shrinking it?
Yeah, it's like it says collapse. So like, is it like super dense in there? Or...
So in this case, it collapses, right? Oh, okay. I thought it was turned on. This good question. What's the average if it collapses? Same. Yeah, if it collapses. Oh, interesting. I was looking at it visually and I didn't read it. I got sloppy. It collapses, and what is the average induced EMF? So it's decreasing. It would still seek to. It's decreasing the amount of field lines. It would still seek to increase it. So it's a similar idea. You're squeezing the area, right? So let's look at it. B times A. So you're decreasing the area. So how does it wants to retain, this is essentially the flux. It wants to retain the flux. How do you make up for the decreased area? You increase the magnetic field lines. So it's a similar argument. The way you want to increase the number of field lines in the center, you do that by creating a magnet or current in this direction. Thanks for pointing that out. Okay? Yeah. Yeah. Direction of the current. This is the wire here, right? And so I'm assuming the current's this way. I may be wrong, right? What I want to do is I want to create more field on the inside of the coil, right? To make up for what's being lost. You're shrinking the area. So you're losing field lines. There's less and less of these field lines as it shrinks. So I need to add more field lines. How do I do that? I need to create a field line from the current. I need to add to those field lines. Let's see if that does that. So the right-hand rule is point, if I'm right, if the current's to the left, the thumb goes in the direction of the current. And then I, what's called curl forward. I always curl forward for this right-hand rule. And the direction that I curl is the direction of the field line. So I'm curling forward. In this case, that means the field line's into the page. And then as far as on this side, as I curl forward, I keep curling. And on the underside, the fingers curl outwards. So on top, they curl in. But as I wrap it around, they curl, the fingers point out. So that's the idea. This is the wire. Assume the direction of the current's that way. And then trace out or just observe which way the fingers point as you wrap them around the piece of wire. On top, the fingers point in. On the bottom, they point out.
Oh, if they were dots instead of X's at the top, you want it to point out.
Yeah, let's do that. Let me just erase it. So you're saying this, right? You're saying this, if there's dots instead of X's? Like that? The point is you want to preserve what you started with, right? So if you shrunk this, you decrease the area. You want to get back to that. So the current have to point in the opposite way. If you did, well, this is the piece of wire. You want to create more field lines on the inside. If the current's pointing that way, when you curl your fingers, as you wrap them up, they're going to point out as you intend. So the current would have to go in the opposite way to preserve the original magnetic field. Yeah.
I'm just telling you. So let's just say for like diagram 1, like on the outside, would there be X's because it's like a conductor? So like it's coiling
On which side are you talking about now? This?
on the outside of the square. Because on the inside,
Yeah.
if it's dots, on the outside it will be X's.
Yeah.
Oh, so it's kind of like a regular like stick.
Yeah, it's because now let's take a look at why is that the case. Let's take a look at the cross section of the wire. So if I were to turn this wire's like this, I were now turn it towards you, cut through it.
Like water.
Yeah, if there was a magnetic field, it would look like this. So let's take that wire. Let's see here. So now with the dots here, it's getting confusing, but with the dots here, I said the direction would change, right? Preserve those dots, it would have to be this way. Current would have to go that way. Now let's take that wire, turn it this way like that. This wire here, turn it like that. Okay. The dot now, the dot indicates the currents, that indicates the currents coming out towards you. Right, I'm just taking that, flipped it like that. The field lines, you draw them in, don't tell me, but draw them in. Which direction would the magnetic field lines be? Around that cross section of wire. Don't tell me, but draw it in.
Like around like the eye.
Yeah, around here. Obviously, it's going to be in circles, but what would it look like in which direction?
It's like going the paper out.
Okay, well, let's see. Thumb points in the direction of the current, that way. Which way do the fingers wrap or curl? This way. So they would be this way. Okay? So you take this, right? What does that represent? That represents this here. So this would be coming out of the page here. Okay, and then into the page here. Assuming you started with out of the page to begin with, yeah.
I'm surprised. So is it like kind of like a reverse solenoid? Because like the wires in the center, but then like the magnetic is circling it. But then like
In a solenoid,
like the yellow.
You
part,
got-
the yellow-
yeah, you got loops, right? Solenoid
the yellow part would be like the magnetic field, and the pink part
looks
would
like this. I'll just draw. If this helps you, let's see. Okay. Make sure I got that right. How to draw these things properly. Keeps wanting to straighten it for me. I don't want you to straighten out. And then same thing as that. Just repeats itself. I can make copies of this.
So is it like,
Yeah, I'm not done yet. Let me just, if this helps you, let's see. So if the current is flowing this way, okay, on the, in front, this is in front. The thicker part is always in front. Right? These are cold wires, coils, wires. So we're interested for a solenoid just as we are here in the field on the inside. Thumb points in the direction of the current. On the inside of these coils, of each coil, on the inside, the fingers curl and point to the left. So the field would be to the left.
I was just trying, so for something like this, the wire creates the magnetic field, but that's for something like one of those wire squares. We're just introducing like a wire square without like a current in it, like to a magnetic field. Right?
Yeah.
But then like it's altering the magnetic field to like spin around.
Are you referring to 3?
Oh no, just like those regular like flux. Like the other squares.
Yeah, it's a different effect, right? If you have a current, it's going to create a steady magnetic field. That's this here, right? You run current through these wires, it'll create a steady magnetic field, okay? If you change the flux, as we did here, you go from here to here, then momentarily, just momentarily, doesn't last forever, you're going to create a current that results in a magnetic field that tries to preserve or get back to what you started with. Momentarily, it won't last. It dissipates. So if that helps. Yeah.
Wait, so this like let's just say the entire magnetic field was originally all X's,
Mm-hmm.
and then you place a wire square on it. Suddenly, all the fields inside the square suddenly turn into dots.
Oh, you reverse the direction.
Yeah, but then like does like I just take a piece of copper wire, put it on there, and then suddenly the magnetic field just changes.
So are you saying, I don't understand what you're saying. If you're saying this, let's make a copy. You're saying you start off with that?
Yeah,
Something like
start
that?
with like an empty field of X's,
X's, okay, sure, X's.
like just an empty field of X's.
And then what does it turn into?
Oh, and then you place a square around those X's, and then suddenly turn to dots.
A square around those X's.
Oh, well, you know, along those wire squares, entire field of X's, and the enclosed area, that's like the flux. And then the flux suddenly reverses.
How does the flux reverse in your scenario? Are you going to change the direction of the field?
No, because like the you said that the inside is like different from the outside always, right?
We're only paying attention to the inside, yeah.
Okay.
The flux only pertains to the field on the inside, yeah.
Is the flux on the inside always different from the flux on the
The,
field on the outside?
the flux is only defined if you have an enclosed area.
And
So we can't talk about this helps you. We can't talk about a flux on the outside because there's not an enclosed area on the outside.
So is the flux on the inside the opposite direction? Is it always the opposite direction to the field on the outside?
Yeah, but you mentioned flux and field in the same sentence.
Okay.
It's like comparing apples to oranges. Yeah. So if you want to talk about the field being, you're talking about the field being in the opposite direction on the outside as the inside. Is that what you're saying? Yeah.
Okay.
Yeah.
As soon as
Yeah, like here it's all dots,
so as
whereas
soon
on the
as-
inside it's X's. Yes.
So just enclosing it causes it to reverse.
Just because of the fact that of the nature of the wire, right? If you look at what do we look? This would be. This helps you. Take a look at this wire. I didn't get to complete this, right? So notice here. Notice here on the right side, the fields point up. On the left side, they point down. What is this? This is just this wire flipped like that. If you took this, right, move in your mind's eye, take this and move it over here like that, what do you get? You get exactly what I drew here. These three here, let me do it in a different color.
How far do those fields extend?
Let me finish. Focus. These three here, okay, represent, it would be like this, so we're clear. What I just highlighted here in green would be this, any of these columns. And then if you want to go further, and then obviously these three here would be indicated by whatever's on the outside.
So what if the eye on the top, the wire on the top also produces a field? Do they like interfere with each other?
No, this is on top.
Like they also
It should produce, I didn't draw it all, but there should be a field pointing out throughout this whole area here.
Then they eventually touch. Do they just like have to figure out at, like
The field lines, they touch. Field lines would just, they would be evenly distributed throughout the area. It all works out. My stomach's still sore. This is not good. Crap.
So when the wire is introduced and then closes the magnetic field, does it have to be charged beforehand? Or
Is the wire, say that again?
does the wire have to be charged beforehand when it is introduced to the magnetic field?
No.
No?
It just has to, there has to be some change in flux in order for a current to be induced. Now, how you change that flux, I can't go through every scenario, but I've given you some, right? You could do what they did here. You could squish it. You could turn it, right? You could actually reverse, as I think you were suggesting. You've got, in this case, the field into the page. You could turn it off, or you could just reverse the direction. In all those cases, you change the flux. And what would that result in? An induced current, EMF and then current. Yeah,
For all the scenarios?
for these scenarios, yeah, that we're looking at. Okay, good questions. Okay, number 4. Find the average EMF induced in a circuit. Okay, just read it to yourself. I'm going through all these thoroughly. Like I said, I'm glad you asked the questions you did, because people tend to have more difficulty with this. So. Okay, so it's important in number 4 you understand what the expression flux changing, I've skipped a couple of words, flux changing at a rate. It's important you understand this expression. I know I skipped a couple of words, but flux changing at a rate of 15, in this case, 15 Webers per second. That's this here. They've just expressed, that's known as the flux changing at a rate, or the rate of change of flux. That's another way of saying it. The rate of change of flux. So you need to understand these expressions. Another way of saying what I just mentioned is rate of change of flux. That's just this. Did I give you that right off the bat? Same thing. I'll just circle it. Okay. So we have the turns, and we have the flux changing at a rate of 15. So that's what I circled there is 15. That's it. That is negative 7.5. Volts. Read over 5. Yeah, it's extra information. Good point. It's extra information. They gave you everything that you need in terms of the rate of change and the number of turns. That's all you needed. It's just an indication of, it helps you understand which direction the current's flowing. So, it's supposed to anyway. Okay, so let's take a look at what we got here. 100 turns times the change in flux. I'll add some more information in a second. 0.12 seconds. Final is 0. And you have the voltage already. So this reduces to that, where you had the magnetic field, right? Do you have the no, you want to find the magnetic field. You have the area. So this area is 4 times 10 to the minus 3. So you're solving for your B. 2.8. Teslas, don't forget the units. Read over 6 to yourself. So this is another common mistake I saw in the lab, actually, when calculating areas, because you did have to calculate areas in that too. Don't forget to convert your meters to centimeters. Your area. Okay, guys at the back, quiet. I wanted a positive answer. Yeah. You just forced it all to be positive. What is the average EMF? Okay. Yeah, well, remember when you calculate area, you have to calculate it using the radius. So, yeah, don't use 25, use half of that. You're welcome. Is the final 0? No, not in this case. Interesting. Okay. Oh, the magnetic field is reversed for the final. Interesting. Okay. So, yeah. The direction is 180. If you look at what it says in number 6, it says the direct magnetic field is reversed. So you're changing your angle from 0 to 180. You're reversing, if you go back to this diagram way up here. This diagram here, I'm going to make a copy of it so I can show you what's happening. You're going from this to, you're changing the direction of the field. So instead of pointing up, it's pointed down. So the angle here is 0. Here, the angle of the field lines with respect to the normal is 180. Okay, that's the difference. So the value is going to be the same except opposite sign. Okay, so the change in flux is final minus initial. So the final is negative. And then the initial is positive. I know there's exponents. Okay, fine, I'll add those in. So you're just doubling it. It works out to be 2.66. That's your change in flux. Negative 2.66. In 0.3 seconds. So you end up with okay, so I would not be overly concerned about what sign you get in front. If you're, it says here, the question is what's the average induced EMF? That's all they ask you for. They're asking you for the absolute value. That's what they want. The sign hints at a change in direction of the, or it's supposed to be a clue as to what the direction of the induced current is. We're not asked for that. So my focus on the magnitude. 7, read that to yourself quietly. Putting 90. They actually give you Teslas per second. Okay, field, fine. Let's say it's 1 second. Fine. Let's say this is for 1 second. We can use that number. We're told, if you look at it carefully, if the problem is read carefully, it says that the magnetic field changes at a rate of 0.5 Teslas per second. So I'm just going to zero in on what the magnetic field is for the 1 second. It's 0.4 Teslas. And I can add that 1 second in at the end. So T, let's make T is equal to 1 second. That's what you start with. Start with 0.4 Teslas. And the area is that's what you start with. And then your final the magnet's removed. So this is 0. If the magnets move, there's no magnetic field. So 0 times anything is just 0. Okay? Remember, we made our time 1 second. $25. Okay, final is 0. This is the final here on top. Minus initial. And the initial is 2. So that works out to be 5. Okay, that's it. Notes. These are notes. These are notes. I'm going to look up pictures, electric generator, because I can. Electric generator. Oh, that's a good one. Anything better? That's a good one. I'm going to make that bigger. I didn't have to draw it. That's a generator, okay? That's a simple version of a generator. What is it? It's, in simple terms, it's a magnet with north and south poles. This would be your axle. Doesn't show it, but it extends out, and you could spin the axle. You'd have to mechanically spin it. Usually you get a motor, you get some sort of gasoline motor to spin the axle. Or you could crank it. Have you ever seen those bikes where you pedal and there's a little generator and the light goes on every time you ever done that? No? Okay, they're out there. Anyways, those are little generators. The point is you have to mechanically spin this. This is an axle. You have to spin it. You have to crank it. I'm not done. There's a north and south pole here. So there's a magnetic field that's pointed from the north to the south. It's cutting through here. So what you're doing, this book represents this coiled piece of wire here. The square loop. It's an enclosed loop, right? So what you're doing is, this is a side profile. The magnetic field lines are pointing this way to the right. Okay, it's parallel, right? No flux, and then you turn it, flux. No flux, flux. You keep spinning it. So what are you doing? You're changing the flux. And if you're changing the flux, what's that going to induce? A current, a voltage, and then current. And that's how the generator works to create a current. What does the generator do? It powers other whatever's in your house. By what? By creating a current, inducing a current when you spin it. Okay? Yeah.
But do you know how they like charge the electromagnets? Because like they have to use electricity to charge the electromagnets, which like they make.
Those are permanent magnets. There are things such as permanent magnets.
Not like in all the motors they use like electromagnets.
They use in some motors permanent magnets. You know, things you play with when you take the north to south pole, right? And they repel each other. They use those in some of the simpler motors. Yeah. Jake, you had a question? Or?
Yeah, so if you look at your bike, you use a safe battery with it.
Could you generate electricity to power parts,
A
things in your?
safe battery with that.
What you mean? Like if you had a battery in your house, could you save? Could you?
You know, with a battery, like, riding your bike.
If you had a rechargeable battery, you could set the rechargeable battery up to the generator, which is generating current that would charge the rechargeable battery. And then you could take that battery and you could power, maybe you could charge your phone with it if you're lucky. You have to pedal for like an hour before maybe you could charge the phone. I don't know. It depends on the efficiency of the generator, but maybe power your phone. I don't know. Maybe generate enough to charge the phone for 20 minutes. That'd be a good experiment, though. It depends how big the generator, depends how fast you're pedaling, how long you pedal for. But yes, you could charge your probably as much as your phone. If you're lucky, not much. You need quite a powerful gasoline motor to generate enough electricity to store in a battery to power the appliances in your house. And even then, you'd have to have quite a lot of gasoline to keep it going throughout the whole week. Yeah? Okay, so the main point is this. You've got inside this generator, you've got an enclosed loop, which we've been talking about. The flux is changing in it. And whenever the flux changes, we talk about Lenz's law, which says if there's a change in flux, nature reacts in such a way as to preserve the original flux. It induces a current to preserve the original flux. So there is a current inside this. I'm going to draw it in yellow. Inside this enclosed wire. And it is enclosed. The enclosure is right there. There's going to be a current generated as it spins. So this is spinning. This is the axis here. It's spinning. This, right? So this is it. The perimeter of this book is the enclosed loop of wire. It's spinning. And as a result of it being spun, there is a current that's being induced. And yes, it does change direction, but that's another point later on. You get what's called an AC current, an alternating current. The current will change directions back and forth, back and forth, back and forth. So there is a current that's induced. Okay, right? As a result of what? As a result of a back EMF. There's a back, to get into that. Anyways, it's generating a voltage which results in a current. Okay? So what we're interested in is this voltage that's generated. It's called a back, we're going to call it a back EMF. What is that? That is the induced voltage which results in a current. The induced voltage as a result of the changing flux. Why is there a changing flux? Because you're spinning the coil. You're spinning this. Magnetic field lines are cutting through it. It's perpendicular, parallel, perpendicular, parallel, perpendicular, parallel, right? So you're changing the flux. So you get a voltage, which then results in the current. Okay, so what we're really focusing on, though, is we'll get to the current later, but we're interested in the back. Call it a back voltage or a back EMF. Okay, so this is called the voltage that's induced, called a back EMF. Okay. Now this is a piece of wire, so it does have a resistance. There's a resistance in it. Every piece of wire has a resistance. A resistance R. Okay. Now normally we would have this. We're going to refer to this as, it gets a little confusing because this is no longer the induced voltage. This is the ideal voltage in this case. That's the original voltage through that coiled wire. What's voltage always equal to according to Ohm's law? IR. Okay. Now, what happens? This is when you're not spinning, before it starts spinning. Before generator starts spinning. Generator. Okay. That's the voltage. That's the current that's passing through the wire. That's the resistance of the wire. Okay, once it starts spinning, what's going to start happening? You're going to get a voltage generated, a back EMF. And that is going to subtract from the ideal voltage. So you got the ideal, and you're going to get a back EMF that subtracts from it. It's going to be in the opposite direction to offset the spinning, or what the spinning induces. Okay? This is the equation when the generator spins. Okay, so here's the confusing part. This makes sense in terms of what's happening. This voltage is subtracting from what you started off with. We usually rearrange this. We rearrange it in terms of the back EMF. So if you rearrange in terms of V back, you get, that's what we want. We want to rearrange in terms of that. So let's just rearrange it. E minus IR is equal to V back. I just put the IR over here and then the V back over here. That's your new equation. That's the way you usually see it written. Okay. Okay. So let's do one example and then we'll take a break. You have a 120 volt, 120 volt motor. That's your ideal voltage. That's your E. Draws 10 amps when it reaches full operating speed. If the coils, and there's more than one coil, I only drew one here. There's more than one in the real motor. If the coils, it's known as the armature, of this motor has a resistance of 5.2 ohms. What is the back EMF? The V back, what is that? Remember, this is the equation. This equation is when, it's important to know the difference. When motor spins, this is more simple than you think. When the motor spins, or there's mention of it spinning, this is the equation you use. When it's not spinning, this is the equation. This is before the generator starts spinning. So when not spinning, when starting up, or not spinning. Okay, so let me just see those two equations. It's really just one equation. Let me show you what I mean by that. That equation there, okay, that's when it's running. Okay. How come it reduces to the simpler version I showed you above? When it's not running, what physically is happening or not happening? When it's not running, the coil is just sitting there. It's not moving. If it's not moving, there's no change in flux. If there's no change in flux, so when not running, there's no change in flux. And therefore, no V back. V back, which is the back EMF, is 0. So what do you get? E minus IR is 0. Okay, it's important to distinguish. This would be, you could call this I2 and this I1. It's a different current. I2, when it's not running, I2 is going to be greater. I2 is the current when it's not running. And then when it starts to run, when it spins, current, because it's a back EMF, the original current is reduced. Because this back EMS, this voltage that's created, results in a current in the opposite direction to subtract from it. This is the current at rest, and this is the current when running. We're almost done here. Let me take a break. Okay, so back to this original question. So what's V back? We're going to use this equation here. V back is equal to what? E. This is the starting voltage, starting or ideal voltage. What you start off with. Not what you end up with. When it starts to run, that voltage will decrease. It's like the voltage of the battery. If you're told that a motor, it's a 120 volt motor, you need that voltage for it to run, to start. Minus, in this case, we're told, go back to the question, we're told it's 10 amps. That would be your I1, right? When it's running. Times, we're told that if you go back to here, the resistance is 5.2. This works out to be 68 volts. What's that voltage doing? It's subtracting from this. In the opposite direction to the voltage of the battery. Okay, so we'll do more when we get back. Take a break. So we're finished. Yeah, just come back at a little bit after 5 after. Yeah.